Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. This session focuses on two important combinational circuits, subtractor and code converter. Combinational circuits, subtractors and code converter. Let me introduce you one of the simpler and most useful combinational circuit. It is based on binary subtraction and the circuit is subtractor. Based on number of input bits to the subtractor, we can classify them as half subtractor and full subtractor. First, we shall see what is a half subtractor. Before that, let us recall the basic rules of binary subtraction. 0 minus 0 equal to 0, 0 minus 1 equal to 1 with borrow of 1, 1 minus 0 equal to 1, 1 minus 1 equal to 0. This basic operation is performed using the logic circuit half subtractor. The half subtractor accepts two binary digits on its inputs and produces two binary digits on its outputs, and those outputs are difference and borrow. To perform subtraction on two binary numbers, what do we do first? Subtracting LSBs of those numbers. What it generates? When 1 is to be subtracted from 0, the result is 1, where 1 is borrowed from the next highest order bit or digit, and we call this bit a borrow, right. So, subtraction of 2 bits, just 2 bits has 2 outputs, a difference and a borrow. Okay. Here shows the logic symbol of a half subtractor. A, B are two binary inputs and difference and borrow are the outputs. Good. Now, let me describe the logical operation of a half subtractor. For that, let us write the truth table of half subtractor. The input variables A and B take the values 0, 0, 0, 1, 1, 0 and 1, 1. Write the output 0, 0, 1, 1, 1, 0 and for the last it is 0, 0. From the truth table, we gather some facts that A and B are the inputs to half subtractor and difference and borrow are the outputs. The borrow output is 1 in case where A is 0 and B equal to 1. From the truth table, we can derive the sum of products expression of the borrow and difference. Do you remember how did we write the sum of products expression from the truth table? We selected only the min terms that produced 1 and ORed them. Similarly, you can write now. Observe the difference output of the truth table carefully. The difference is 1 when A equal to 0, B equal to 1 and when A equal to 1, B equal to 0. So, the corresponding min terms are A complement B and A B complement respectively. So, logical expression for difference is difference equal to A complement B plus A B complement. The borrow is 1 when A equal to 0 and B equal to 1 and the corresponding min terms is A complement B and that itself is the expression for borrow. So, borrow equal to A complement B. Notice the expression for difference once again. Difference equal to A complement B plus AB complement. Can you recall this expression? This is the logical function of XOR gate. So, difference output of a half subtractor can also be expressed as the exclusive OR of the input variables. Therefore, we write difference equal to A XOR B. Borrow output is the same A complement B. Now, let us design the half subtractor with XOR implementation. The inputs A and B are connected to an XOR gate to output the difference and the same inputs are fed into an AND gate to output the borrow. Hope all different aspects of half subtractor are clear to you. Then next we dive into the concepts of full subtractor. Full subtractor. What is full subtractor? It is a combinational circuit that performs binary subtraction of 3 bits. The full subtractor accepts 3 binary digits on its inputs and produces 2 binary digits on its outputs, and those outputs are difference and borrow. Logic symbol of a full subtractor is given here. Here we can see 3 inputs, A that is minuend, B that is subtrahend, and borrow in that is previous borrow. The 2 outputs difference and borrow out are the difference and the output borrow respectively. Now, let us form the truth table of subtraction of 3 bits. We get the values as inputs 0, 0, 0, then the subtraction result, that is difference and borrow, are 0, 0. Then 0, 0, 1, it is 1, 1. For 0, 1, 0, it is 1, 1. It goes like that. If inputs A equal to 0, B equal to 0 and borrow in equal to 0, output difference equal to 0 and borrow out equal to 0. This is obtained by binary subtraction, 0 minus 0 equal to 0. It gives difference 0, borrow 0. If inputs A equal to 0, B equal to 0 and borrow in equal to 1, output difference equal to 1 and borrow out equal to 1. It is obtained by binary subtraction, 0 minus 0 minus 1. That gives difference 1 and borrow out has 1. If inputs A equal to 0, B equal to 1 and borrow in equal to 0, difference is 1 and borrow equal to minus 1, and this is obtained by the binary subtraction 0 minus 1 minus 0. That gives difference 1, borrow out 1. If inputs A equal to 0, B equal to 1 and borrow in equal to 1, the difference is 0 and borrow out equal to 1. Again, if inputs A equal to 1, B equal to 0 and borrow in equal to 0, the difference is 1, borrow out equal to 0, and it goes like that. Now, let us deduce the sum of products expression for the outputs, difference and borrow out using K-map. Draw the K-map for the output function difference. From the truth table, we see that the input values 0, 0, 1, 0, 1, 0, 1, 0, 0 and 1, 1, 1 produces 1 for the difference output. Mark them in the corresponding cells of the K-map. No groups are formed. So, the minimum SOP expression for difference D is A complement B complement B in plus A complement B B complement in plus A B complement B complement in plus A B B in. Difference is equal to A complement B complement B in plus A complement B B complement in plus A B complement B complement in plus A B B in. Then draw the K-map for the output function borrow out. The input values 0, 0, 1, 0, 1, 0, 0, 1, 1 and 1, 1, 1 produces 1 at the output borrow. Map the ones. We get 3 pairs and the sum of products expression for borrow out can be written as A complement B plus A complement B in plus B B in. Now, we have the SOP expression for sum and carry as difference equal to A complement B complement B in plus A complement B B in complement plus A B complement B in complement plus A B B in, and borrow equal to A complement B plus A complement B in plus B B in. Notice the expression for difference once again. Difference equal to A complement B complement B in plus A complement B B in complement plus A B complement B in complement plus A B B in. Can you recall this expression? This is the logical function of XOR gate. So, difference output of a full subtractor can also be expressed as the exclusive OR of the input variables. The input variables are A, B, B in. Therefore, we write difference is equal to A XOR B XOR B in. Borrow output is the same, A complement B plus A complement B in plus B B in. Now, let us design the full subtractor with XOR implementation. In the above figure, B in is represented as C. The next, construction of full subtractor using half subtractor circuit. You see the figure, we can see two half subtractors that are combined using an OR gate. The first half subtractor has two single bit binary inputs A and B, and the first half subtractor produces two outputs, that is difference and borrow. The difference output of the first subtractor will be the first input of the second half subtractor, and the borrow output of the first half subtractor will be the second input of the second half subtractor. The second half subtractor will again produce two outputs, difference and borrow. The final outcome of the full subtractor circuit is the difference. How we can find the final output of the borrow? For that, provide the borrow outputs of the first half subtractor and the second half subtractor into the OR gate. The output of the OR gate will be the final borrow of full subtractor circuit. We have already seen how a half subtractor function is implemented using XOR function. Now, this can be easily extended to implement a full subtractor. See how the difference is implemented. Initially, perform the XOR operation on inputs A and B. We obtain A XOR B. Perform XOR again on this output with borrow in. It generates the final difference output A XOR B XOR B in. How do you get B out? Borrow output. Inputs of first half subtractors are A and B. Its borrow is A complement B. What are the inputs of second half subtractor? A XOR B and B in. So, borrow from second half subtractor is A XOR B dot B in. The logical sum of these two borrows gives us the final borrow output, that is A complement B plus A XOR B dot B in. With this, we completed 2 bits and 3 bits subtraction. Code converter. What is a code converter? As the name indicates, it is a combinational circuit used to convert one type of code to another. We have already learned binary codes such as BCD code, XS3 code, gray code, etc. To convert from one code to another code, we use code converters. In order to understand how to design a code converter combinational circuit, let us take an example of binary to BCD code converter. What is a binary to BCD converter? The circuit will take binary number as input and will produce corresponding BCD code as the output. What is a BCD code? In this code, each decimal digit is represented by a 4-bit binary number. BCD code is a way to express each of the decimal digits with a binary code. Let us recall the binary to BCD code conversion. Consider the example 12. What is the binary representation of 12? It is 1100. Let us represent this in 8 bits. Then 12 can be represented as 00001100. Now, what is BCD code of 12? 0001 0010, that is in BCD. 1 will be represented in 4-bit binary, then 2 will be represented in 4-bit binary. If we are considering a 4-bit binary number, we have 2 raised to 4, that is 16 combinations are possible. So, we need 8 bits for representing corresponding BCD output. But first 3 bits will be 0 for all the BCD output combinations. So, let us avoid those 3 bits and consider remaining 5 bits for output. Let us consider the truth table of BCD converter. The binary code is represented in the first 4 columns A, B, C, D. It takes the values from 0, 0, 0, 0 and BCD code is represented using the next 5 columns W, X, Y, Z, E and starts with the values 0, 0, 0, 0, 0 and both ends with the values 1, 1, 1, 1, 1 in binary and 1, 0, 1, 0, 1 in BCD. Let us draw the K-map for each outputs W, X, Y, Z and E. K-map for output W. Consider the column of W in the truth table. Mark 1 in K-map where W is 1 in the truth table. Here we have two quads. We can write equation from K-map as W equal to AB plus AC. Similarly, we can draw K-map for output X. Consider the column of X from the truth table. Mark 1 in K-map where X is 1 in the truth table. We have only two ones that are in 8 and 9. We have a pair here. So, X equal to A, B complement, C complement. Now, consider the next output column Y. Let us draw the K-map for Y. Here we have two quads. Hence, the output Y can be represented as Y equal to A complement B plus BC. Similarly, we can draw K-map for output Z. Consider the column of Z from the truth table. Mark 1 in K-map where Z is 1 in the truth table. Here we have one pair and one quad. Let us write the equation of Z from K-map. Z is equal to ABC complement plus A complement C. Now, last output column E. Let us draw the K-map. Here we have one octet and hence E equal to D. Now, we have equations for all the 5 output bits W, X, Y, Z and E. What are they? W equal to AB plus AC, X equal to AB complement C complement, Y equal to A complement B plus BC, Z equal to ABC complement plus A complement C and E equal to D. Now, based on these 5 output bits equations, let us design the logic circuit of BCD converter. Now, consider the same example of 12. 12 is represented as 1100 in binary. Here A equal to 1, B equal to 1, C equal to 0 and D equal to 0. Let us find out the output bits W, X, Y, Z and E using the designed binary to BCD converter. W equal to AB plus AC, which is equal to 1.1 plus 1.0, which is equal to 1. X is equal to AB complement C complement, that is equal to 1.0.1 equal to 0. Y equal to A complement B plus BC, that is equal to 0.1 plus 1.0, we get 0. Z equal to ABC complement plus A complement C, which is equal to 1.1.1 plus 0.0, that gives you the answer as 1, and E equal to D, which is equal to 0. Now, the output W, X, Y, Z, E is 10010, which is the BCD equivalent of the binary 1100. Hope that you are clear with binary to BCD converter circuit design. Similarly, we can design any code converters. Now, let us summarize the topics we discussed here. We discussed about two important combinational circuits, subtractor and code converter. The subtractor circuit is very similar to the adder circuit which we studied in the previous class. So, you might have found it easier to understand. In the code converter circuit, we converted a binary number to its equivalent BCD code. Let us continue with more combinational circuits in the coming sessions. Thank you for watching. See you in the next session. Bye.